Now, as you can see in equation 20, again, take a look at equation 20 again. You're supposed to have 3 summation sign. Then multiply with f, and then multiply with something to do with w raised to a certain power, as you can see from equation 19. So after you simplify equation 20, because the square bracket is equal to 1, what you can see in equation 21 is the same thing. You see, you have 3 summation signs, like I told you, corresponding to the index k0, k1, and k2. And then you have a function f, and then multiply with w raised to a certain power, like I told you. All right. Then the next thing we say is this. We can calculate the unknown vector c tilde n2, n1, n0 by systematically calculating the right hand side of equation 21. And the way to do that is we define the first bracket right here. We call it, that is, the whole thing here is the intermediate vector f1. As a matter of fact, you can see that definition is right here. You see? So the definition of f1 is given in equation 22. Okay? Now, assuming equation 22 is applied, you already saw for f1. The next thing you can do is you take the summation on k1 of f1, and then you multiply that with this term right here. Together, we call it f2. And that is exactly shown in equation 23. So the procedure basically is, first you calculate f1 based on the definition shown you in equation 22. Then after that, you know f1, you multiply with this wf, right, w term right there. Together we call it f sub 2. And then finally, knowing f sub 2, you take the summation on k0, you time f sub 2, and then you multiply with this last term for w, and that will give you f sub 3. You see? So it's just like here, you calculate the intermediate vector corresponding to level 1 that I talked to you earlier when we talk about the informal development of the fast Fourier transform. Here, we're talking about the computation of level 2 for the vector f2. And then finally, we talk about computation for vector f3 for level 3. And when you finish that, you will get the value for f3, which in the order of n0, n1, n2. But that order is exactly reversed from the order of the vector c tilde that you would like to have. And that's why you have to go through the reverse bit order process, or we call unscrambling process. Okay? So as I told you, by the end, after you calculate the intermediate vector f3, after we calculate the vector f3 in terms of n0, n1, n2, you see, after you calculate f3 according to the order of n0, n1, n2, that should give you the same answer as the unknown vector c tilde, except that you have to reverse the order of this in order to get the order as n2, n1, n0. So let's take one more remark about equation 22. So let's take a look at equation 22. That equation 22, as you can see, it is shown in here. Equation 22. Basically, calculate the intermediate vector F1. However, as you can see, to calculate the computational vector F1, you have to calculate several components of the vector F1, and those components depending on the value of n0, k1, k0 that you have to define. Remember now, n0, k1, and k0, the value of each of these guys could be either 0 or 1 only, and which means you have a lot of different combinations. Like for example, you can let n0 equal to 0, k1 equal to 0, k0 equal to 0. You get one term of F1. Then you let n0, k1, k0 have a different value, so you can have a lot of different combinations. So take a look at some example. If you look at equation 22, like I told you, and again, when you look at equation 22, notice one thing. In equation 22, you have to calculate F1 based on the value n0, k1, k0. All right? So you see, equation 22, you're supposed to calculate F1 depending on the value of n0, k1, k0. So one thing you can see, the value of n0 could be either 0 or 1. The value of n0 could be either 0 or 1, the value of n0. Okay? The value of any index can only be either 0 or 1. So now, let's say, suppose after that, we say n0 equal to 0 or 1, okay? Then after that, we say, what could be the value for k1 and k0? Well, the possible answer for k1, k0 could be either 0, 0, or 0, 1, or 1, 0, or 1, 1. So what it means is that equation 22a can be expanded in terms of 4 equations, like I show you in equation 22b. Now actually, you can expand that to be more. Notice one thing. According to equation 22b, you will see the computation of this term, which is F1 of 0, 0, 0, that we show you here by the double star. If you compare to the next computation of the term, let's say F1 of 1, 0, 0, that we also show here with the double star. If you notice it, they both are very similar. Why? Because you can see, in order to calculate F1, 0, 0, 0, the formula say it is equal to F0, 0, 0 plus F1, 0, 0 times W raised to the power 0. The computation of the next guy with the 2 star in the next slide, they're exactly the same. The only difference is this plus sign become the minus sign. And you can see from the next slide. You see, the computation, this one is the same thing as F0, 0, 0, and this product is the same. The only difference is the plus sign up there become the minus sign here. Well, this should not be a surprise to you, and the reason is because these two nodes that I indicated with the star, double star there, they are companion node. So, in other words, the procedure works like this. You calculate F1, 0, 0, 0, and the computation of this guy can be skipped. And the reason is because the computation of F1, 1, 0, 0 is the same thing like before except the minus sign, you know. Similarly, after you compute, let's say, the computation of F1 001, if you compute this one, then the computation of this term, which is F1 corresponding to 101, can be skipped because the formula is the same except the plus sign now become the minus sign. So to summarize it, what it means is you compute the first 4 equation here, and you can skip the next 4 equation which I show you in here. I say you skip it but actually you compute it at the same time when you compute this guy in here, with the only plus become a minus. That's what I mean. So to summarize it, in this